A grade 9. Dropping to an 8, dropping to a 7. Right there. That is the exact sound of your Cambridge 0625 physics grade slipping away right in front of your eyes. And the craziest part? It is not because you don't know the physics. It's because you don't know the exam. You're walking into the hall blind to the trapdoors. So today, we are tearing apart the mass, weight, density, pressure, and resultant force questions from the forces paper, and I'm going to show you exactly how to lock down every single mark.
Okay, let's dive straight into this deceptively simple calculation where top students completely, and I mean completely, sabotage their own grades. Picture this. A student calculates the density of a block as 2.456 grams per cubic centimeter. They confidently write down 2.4 on the final answer line, they smirk, and they move on to the next page. So what fatal mistake did they just make? Take a guess.
2. That is the number of marks you instantly lose for rounding too early and presenting an answer without checking the required significant figures and units. Poof, gone. In Cambridge physics, 2.456 rounded to two significant figures is 2.5, not 2.4. And even then, you have to ask yourself, is two significant figures actually what the question asked for? Did you check the data in the prompt? Leaving those marks on the table is just brutal. I've got to confess something here. Seeing brilliant students lose vital grade boundaries over simple terminology and formatting mistakes is literally the most painful learner mistake out there. It hurts to watch. You spend hours, days even, memorizing the density equation, but you drop the ball on the final hurdle because ordinary revision fails to teach you the rigid rules of the examiner's mark scheme. We can't just guess what the examiner wants. We need a repeatable, bulletproof strategy for every single force, pressure, or density question they throw at us.
Section 1. The top band answer framework.
Now, what's really interesting about this is how it breaks down the exact formula Cambridge examiners use to award full marks. It's not magic, it's a 4-step framework. Number 1, state the underlying physics concept. Number 2, pull exact evidence or data directly from the question. Number 3, apply scientific reasoning to connect that raw data to your concept. And finally, number 4, package the whole thing using safe, examiner-approved wording. This is your engine. This is how you generate marks on demand.
Section 2. Fixing flawed forces answers.
Let's move to a practical example and see how this builds our score in real time. The crucial point is comparing the vague answer on the left with the precise equation-backed answer on the right that actually fulfills the command word requirements. The flawed answer says the pressure increases because the force is bigger and the area is small. I mean, it's essentially true, sure, but it is entirely unscientific. It's fluff. Now look at the top band answer. It states the concept, pressure increases. It gives the evidence, the equation P equals F over A. It uses scientific reasoning, the same resultant force applied over a smaller contact area. And it finishes with the correct examiner wording and units, newtons per square meter. That right there is how you construct a top band response. So to recap the traps, these are the 4 most common pitfalls students fall into during mass, weight, density, and pressure calculations. Missing units on final answers. Rounding values way too early in intermediate calculations, which totally skews your final number. Giving vague explanations without proper terminology, like saying bigger instead of greater resultant force. And finally, stating conclusions that just aren't supported by the data provided. Write these down, internalize them, make them your mental checklist.
But wait! There's a massive hidden trap regarding experimental graph anomalies that changes your entire conclusion. In a moment, I'll show you the exact examiner clue regarding practical graphs that literally flips an answer completely. But first, you need to spot the flaws in the raw data itself. Because think about it, if you can't read the data table correctly, your graph is going to be doomed from the very start.
Section 3. Practical investigation traps.
Let's apply our framework to a classic Cambridge-style resultant force and motion investigation. These practical questions, man, this is where the boundary between an A and an A star is usually decided. Look closely at this typical student table, measuring mass, resultant force, and acceleration. A student sets up an experiment, measures the force applied to different masses, and records the resulting acceleration. Scan these numbers. Really look at the columns.
Take a second to mentally red pen this data. What did the student do wrong with their variables and recordings? Pause and predict. If you were the Cambridge examiner holding the red pen, where are you deducting marks before this student has even plotted a single point on a graph? All right, time's up. This brilliantly illustrates why students lose marks. They miss the anomaly, they drop their significant figures, and they completely botch their graph axes. Look back at the force column. We had 1.0, 2.0, then just 3, and 4.0. That is inconsistent significant figures, and examiners hate that. Then, look at the acceleration column. 9.8, 9.81, 12.5, and 9.79. That 12.5 is a glaring anomaly. If a student plots that on a graph without identifying it and drawing a proper line of best fit that ignores it, their entire conclusion about the relationship between force and acceleration is absolutely ruined.
Before you can even begin to evaluate anomalies like that or suggest practical improvements, you need absolute clarity on the core concepts. Using exact, exam-safe definitions like this is your baseline defense. Resultant force is the single overall force acting on an object, found by combining all individual forces, which determines the object's acceleration or deceleration. Don't paraphrase this. Memorize this exact phrasing. It's your anchor.
Section 4. The ultimate checkpoint.
Now it is time for a harder example, escalating from just spotting data errors to actively creating practical improvements. The exam will inevitably ask you how to make an experiment more accurate or reliable. And let me tell you, saying, "Be more careful when reading the spring balance" is the most common, useless answer out there. It means absolutely nothing to an examiner. It's empty. Notice how the top band answer shows true mechanical understanding. You name the specific error, parallax. You give it scientific action, read at eye level. And you improve reliability, repeat the experiment to find a reliable mean. This is how you secure those top marks.
This examiner-style feedback proves that you cannot just guess. You must use your evidence and scientific reasoning. When the examiner writes their report at the end of the year, this is exactly what they complain about: weak practical improvements and completely ignoring the actual data trends sitting right in front of them. Please, whatever you do, don't be the candidate they are talking about here.
So make this your mandatory checklist before you move on from any mass, weight, density, or pressure question. Number 1, have you substituted your values with the correct units? Number 2, have you checked that you didn't round your numbers too early in the calculation? Number 3, are your graph scales and gradients consistent? And number 4, for practicals, have you addressed uncertainties and safety? If you can confidently check these 4 boxes, your answer is pretty much bulletproof.
Okay, so you now know how to fix basic forces answers, how to spot data anomalies, and how to provide top-band practical improvements. You're bridging the gap to that target grade. But what happens when the exam throws a high-mark evaluate question at you using a completely unfamiliar experiment? You know, the ones that just freeze you in your tracks the second you turn the page. To truly lock in those top boundaries, you absolutely must know how to decode the toughest evaluation command words. We are going to continue this correction sequence and break down that exact framework in our next explainer. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCE to excel in your Cambridge examinations, and click the explainer on your screen right now to master the top band evaluation framework. I'll see you over there.